Okay, so now we've sort of been dancing around it here. We have this very quantitative way of talking about solutions, all right? And that is in terms of what's called concentration. And this is a concept that you were kind of lightly introduced to in Chem 1A, and we're going to sort of do a deep dive here. Concentration is simply a measure of how much solute. Yeah.
So solubility is when you mix when chemicals mix together or like when they break off.
It's the maximum amount that you can get to dissolve in a given solvent.
So if temperature increases, wouldn't it be more soluble?
That's true for solids. It is not true for gases. Yeah. And the thing is at temperature, things move around more. Those gas molecules are able to collide and form little bubbles and escape. So for gases, it's an opposite sort of trend as what we saw for solids. Okay, so concentration is a measure of how much solute is in a solution. Okay? And to make things extra fun for Chem 1B students, we actually have many different ways that we could measure concentration. There's not just kind of one way. There's a few different sets of units that we could use, all of which are telling you the same piece of information. They're all telling you how much solute there is in a solution. Okay? But there are a few different methods that we're going to learn here. The one that chemists really love, the one that we default to, the one, honestly, that I only ever used in my 10 years of research experience is what's called molarity. Molarity is represented with a big M and stands for moles of solute per liter solution. So moles per liter. That's why chemists love it, because chemists love talking in terms of moles. That's how we quantify chemical reactions, right? So we love moles in chemistry. All right. The other one, it's fairly similar, is molality. All right. Molality is represented with this like fancy italics lowercase m. So I'm going to try to do my best job of being fancy, but like an italicized lowercase m for molality. Molality is also moles of solute, but now per kilogram solvent. Okay, so notice not solution, but just how much solvent you're using in your mixture. All right, and then the last one is what's called a mass percent. Let me get rid of this random squiggly line. Okay, this is now grams of solute per gram solution times some factor F. Okay, I'll talk about that here in a second. But let's just note that both molarity and mass percent are quantifying how much solute there is per solution. And then molality is kind of an oddball. It's not talking in terms of kilogram solution, but kilogram solvent. Okay, so just something important to keep in mind. So this factor F, you can talk about mass percents in a few different ways, and I'm sure you've sort of seen these. One of it is just straight up percent, like our percent symbol. And this is when F has a value of 100. right? So just kind of like our normal percentage scale that you're used to. Other industries that talk about concentrations, in particular the health field, nursing and doctors, they don't give a crap about moles, right? But they still need to use concentrations quite often, right? They have these solutions of drugs. They need to know how much to give a certain patient that weighs a certain amount. They almost exclusively talk in mass percent. Because again, they don't really care about moles. That's a very chemistry specific thing, but they still need to talk about concentration. So this is something that you see a lot outside of the field of chemistry and in particular in health fields. If you go in your medicine cabinet and you look on the back of like your nail polish remover, you will see the concentration in this percent mass. Okay? The other ones that's used mainly for very teeny tiny amounts, specifically if you're like talking about the amount of lead that's allowed to be in drinking water or something like that, would be parts per million. Okay, this is where F takes a value of 1,000,000. Or even smaller, parts per billion, where F takes a value of 1,000,000,000, 10 to the 9. F is this constant in our equation here. So you take the grams of solute divided by the grams of solution and you multiply it by 100 if you're talking about percent mass. You multiply it by 1,000,000 if you're talking about ppms. And you multiply it by 1,000,000,000 if you're talking about ppb. Okay? So these are these three ways that we're going to talk about our concentration here in this course. We want to be able to use these different concentrations. All right, so let's start sort of simple here. All right, let's try to figure out what is the molarity of a solution created by dissolving 0.50 moles of NaCl into 2.5 liters of solution. Okay, so first of all, molarity, we got to remember our definition for molarity. That big M stands for moles of solute over liters solution. So we're going to plug our 0.50 moles of NaCl and divide that by our 2.5 liters of our solution. Okay, my calculator spits out 0.2. Okay, what's my units? That big M, molarity, right? So moles per liter, you could write moles over liters or just the big M for molarity, right? So here's my units. What about my sig figs? How many sig figs should I have? I need 2, and how many did my calculator give me? Just 1, so what am I gonna have to do? Tack a 0 on the end. Okay? And let me just show you some other symbology that we use for concentration here. You would see this written as bracket NaCl equals that value. The brackets stand for concentration of whatever's inside in molarity. Okay? So you'll see this bracket notation a lot. It's something that's unique to chemistry. But this bracket notation here means the concentration of NaCl in molarity. Okay? Cool, so if you got moles and liters of solution, you're going to divide the moles by liters because that's molarity, right? Let's do a slightly more difficult one here. What is the volume in liters of a solution where bracket NaCl equals, move this down here, 3.5 molar that contains 0.29 moles of NaCl. Okay, so I have this bottle here of sodium chloride that's 3.5 molar, and I need 0.29 moles of sodium chloride in my experiment. I need to know how much of this I need to pour into my beaker and take over and do my experiment, right? That's what we're trying to solve here. What volume of this solution should I be using that accounts for that 0.29 moles, okay? So here's the trick with these concentration problems. I need to know how to take this piece of information, my concentration, and turn it into something that I can actually use in my math, okay? 3.5 big M, that's not how it's gonna look when we set up our math here, all right? What we're gonna do, this 3.5 big M, this is how we represent it in our problem. How we use it in our math is to stack moles over liters. So this is going to turn into this conversion factor here where I have 3.5 moles of, in this case, NaCl over 1 liter solution. Remember, that's what that big M stands for, is how many moles per liter you have. So I haven't changed anything. I've just restated that term. But importantly, I've put it in a way that we can actually use in our math. And by that, I mean we're going to see our units cancel out beautifully, and everything's going to work out the way that it should. Okay? But this is the tricky part. How do you take this piece of information from your problem and convert it into something that you can actually use in your math? Again, we're going to take those moles, stack them over liters. Okay? So this is what we're going to be using in our math here. My problem gives me this 0.29 moles of sodium chloride. So let's put that out front here. Okay? So now I'm going to have to use this term right here, right? So we said we built it in such a way that we can use it in our math. Am I just going to multiply it as is? What's the problem? My units don't cancel out. So what am I going to have to do? Flip it, right? I can always use these conversion factors as is or flip them. So instead of multiplying by that 3.5, I'm going to divide by that 3.5, right? So I'm going to set this up in such a way that that 1 liter of solution is on top, and that 3.5 moles of NaCl are on the bottom, right? And we can tell that it's set up correctly because our moles of sodium chloride cancel out, and we're left with our volume of solution, our liters of solution, okay? So punch this into our calculator. Get 0.082857. blah, blah, blah. And again, what are my units? Liters, right? My moles of NaCl have canceled out. I'm left with liters of solution. All right, and then my last step, sig figs. How many sig figs am I going to round to? 2. So final answer, 3 liters of my solution. That's how much I'm going to need to take from my big bottle in order to do my reaction that requires 0.29 moles of that solute, of that sodium chloride. Okay? So this is going to be the trick for all of these solution problems. You're given this concentration information in your problem, 3.5 molar. You need to make sure that you know how to turn this into something that we can actually use in our math, stacking one of those units, the moles, over the liters. Right? And we're going to play the same game for all of them. It's just that if we're talking in molality, it's not moles over liters, it's moles over kilograms of solvent. Right? If we're talking in terms of percent mass, it's grams of solute over grams solution, et cetera, et cetera. Okay? All right, let's do another one here. Yeah, what's up?
So I did 3.5 equals 0.294x. Would you have to do it the long way, or?
No, the cross-multiplying method works for these simpler problems. If we're starting to if you also then had to convert to milliliters or something like that, I always teach my math in this very stoichiometry sort of setup way. Truthfully, there's a lot of different algebraic ways that you can solve a particular problem. I always teach this one because it works time after time for whether we're talking about chemical reactions or concentrations or unit conversions. So yes, a cross-multiplication method would work for this particular thing. And we get to more complex sort of multi-step, you'll have to then break it up into a bunch of chunks. Okay, so let's see, based on what we just learned here, let's see if we could figure out the following problem. All right, I'm going to give you guys a few minutes to attempt this one on your own. Okay, we want to figure out how many moles of potassium chloride are in a 4.26 molal solution containing 2.5 kilograms of solvent. And again, your first step is to take this piece of information right here and turn it into something that you can use in your math, stacking one set of units over the other. All right, so everybody take a minute, see if you can't do this one on your own based on what we just did in the previous problem. All right, so everybody take a second and introduce yourself to your neighbor. It's going to be a little awkward. Hey, hi, how are you? Awesome. So when we break in and do practice problems, your neighbor is a great way to check to see if you're on the right track, all right? So check in with your neighbor, see if you're getting the right same answer, is everything set up the same, et cetera, et cetera. All right, should have gotten 11 here, so let's work through this, all right? First of all, I got to take this and turn it into something that I can use in my math, my 4.26 molal. What is the definition of molal? Moles of solute over kilograms solvent, right? So now we're not using molarity anymore, but that molal. So this 4.26 molal corresponds to 4.26 moles of KCl over 1 kilogram of solvent. So this is what I'm going to be using in my math here. All right, so now I'm going to start. I start with 2.5 kilograms of solvent. All right, am I cool with this term as is, or am I going to have to flip it? It's good, right? I got kilograms on the bottom. Everything will cancel out. So now I'm going to multiply that 2.5 by that 4.26. Okay. Punch that into my calculator. I get 10.65. My units cancel out nicely. So that I'm left with, whoa. So that I'm left with moles of KCl. Okay. And then how did I get 11? My concentration has 3 sig figs. But what about my mass? Got 2, right? So 2 sig figs, 3 sig figs. My final answer can only have 2 sig figs. So final answer, 11 moles of KCl. And I guess just to be clear, in case anybody was confused, whenever we're stacking it on, over, this 1 here is considered to be exact. Same with our molarity. We're not limited to 1 sig fig by that 1. That 4.26 molal, all the error is in that 4.26. The 1 is considered to be exact in that calculation. What's up? When you're multiplying, yeah, it's this number times this number, whichever one of your input has the fewer sig figs, your answer should have that many sig figs.
Is it different for division?
Yes, not for division. It's different for subtraction and addition. Okay, we'll review that when we get to it here. All right. So then let's use our percent here. Okay. We can how many grams? Okay? So we're going to play the same game here, but these percent mass ones are a little bit trickier. So let me show you real quick how I would take 26.7% mass and turn it into something that we can use in our math here. Okay, let's remember that our percent mass is when I take grams of solute divided by grams of solution times F, which for percent mass is 100, like a normal percentage. Okay, but how we're going to use this in our math is this is going to become 26.7 grams of NaNO3, grams of solute, so nothing weird yet. But since it's a percentage and we multiplied by that 100, this is the number of grams that are in 100 grams of solution. All right, not just one, we multiplied it by that 100 to get our percent, so that number here is how many are in 100 grams of solution. And in general, we can sort of just make a note for these mass percents when we use them in our math. And let me kind of make room here. Okay, so in our math, this is going to become grams of solute over F grams of solution. Right? Since we were using percent mass in this problem, we took it over 100 grams. If instead we were using parts per million, we would take it over 10 to the 6 grams of solution, right? So whatever that value of F is depending on your units, again, in this case, we were using percent mass. That's why we took our 26.7 grams and divided it by 100 grams of solution. Okay? So now that we got this far, everybody take a second and work through the rest of this problem here. All right, so I'm going to start with my 14.5 grams of sodium nitrate. Okay, I'm going to be using my concentration here. Is it good as is, or am I going to have to flip it? I'm going to have to flip it so that my grams, my 26.7 grams of sodium nitrate are on the bottom, and that 100 grams of solution are on top. Okay, so I'm going to be dividing by that 26.7 and then multiplying by 100 to give me 54.3071. What are my units? Gram solution. Okay. Again, like we said, the thing that we put on the bottom here, this 100 in this case is exact. So then how many sig figs am I limited to in this problem? 3. All right, 14.5 has 3. 26.7 has 3. So my final answer here will be 54.3 grams of solution. That's how much I'm going to need if I need 14.5 grams of my solute, my sodium nitrate. Okay? So again, the key here in these problems, making sure you can turn what you're given in your problem into what you're actually going to use in your math. Right? And then it's all about same game as you played a whole bunch in Chem 1A. Pay attention to the units, make sure everything cancels out, and you're left with what you want. Cool? All right. Okay. How many grams of solution contains 16.5 grams of magnesium chloride if the concentration of that solution is 25.4% mass of my magnesium chloride? Okay, and so step 1 here is going to be the same. I'm going to need to convert my percent mass into something that I can use in my math. All right, but because of that factor, that F, it's going to be a little different from these other ones. So let me show you how to do it for these percent masses here. 25.4% mass is that 25.4 grams of my solute, okay? But because it's a percent mass, it's not in 1 gram of solution. This would be in 100 grams of solution. Right? Because it's a percent, because we took that ratio and we multiplied it by that 100. Okay? So in general, if we go back to our definition page here, we have all these definitions, right? If we're going to use these in our math, how we're going to do it is put grams of solute over F grams of solution. In this case, it was a percent mass, so I put it over 100 grams of solution. If I was talking in terms of parts per million, I would put it over 10 to the 6 grams of solution, right? Whatever that factor of F is, that's going to be in your denominator. Unlike molarity, we just put it over 1, all right? But for these mass percents here, because we're multiplying by that factor F, we have to account for that. And the easiest way to do it is to stack your grams of solute over F grams of solution. Okay, where again, F depends on whether we're talking about percent mass, parts per million, or parts per billion. Okay? Okay, so given that, I believe in y'all. Finish this off for me. so starting with my 16.5 grams of magnesium chloride, I'm going to need to use my concentration here, 24.5 grams of magnesium chloride over 100 grams of solution. Am I going to use it as is, or am I going to have to flip it? I got to flip it. So my 25.4 grams of magnesium chloride are on the bottom. My 100 grams of solution are on top. So I'm going to take 16.5, divide it by 25.4, then multiply it by 100. So my calculator spits out 64.9606, blah, blah, blah. My units, grams of magnesium chloride, cancel out, and so I'm left with grams of solution. Okay? Let me just note here, and this was true, I didn't actually explicitly say it before, but when we look at, for example, our molality, this number has 3 sig figs. The one on the bottom, we always consider to be exact. All the error in that concentration is sitting in that top number. Okay? So same thing here. It might be tempting to look at this block of math that I can't find. There it is. Right? This 100, if as written, would have 1 sig fig, but again, since it's what we're putting in our denominator, this is considered to be an exact number. So my initial mass has 3 sig figs. My concentration also has 3 sig figs. So I'm going to round my answer here to 3. So how does this round to 3 sig figs? I got to round that 9 up, right? So this would become 65. And what do I got to do? 0.0, right? When you say rounding to 3 sig figs, that means the number that you give me at the end better have 3 sig figs, right? So 65.0 grams of solution. Okay, so again, with these percent masses, the trick here is that you need to put not just 1 gram of solution, but 100 if you're talking about percent mass, 1,000,000 if you're talking about parts per million, or 1,000,000,000 10 to the 9 if you're talking about parts per billion. Okay, so let's just practice one more of those. Okay, the safe level of arsenic in drinking water is 0.10 parts per billion. Okay. How many grams of arsenic can safely be in 250 grams of solution? How do you turn this into a piece of information you can use in your math for parts per billion? Right? That's always our first step. Take that concentration, turn it into one of those terms we can use in our math. parts per billion means we got 0.10 grams of our solute arsenic over 10 to the 9 grams of solution. All right, that factor F for parts per billion was 10 to the 9. And so when I build my math here, I'm going to put my grams of solutes over F grams of solution over those 10 to the 9 grams of solution. Is 10 to the 9 a big number or a little number? It's a massive number, right? So that's a very tiny amount of arsenic that's allowed to be in our drinking water, right? And that's what parts per billion is good for, is representing those small quantities. And now, of course, I've lost my page. Oh, phew, okay. All right. And so if we start out with our 250 grams of solution, we're going to multiply it by that concentration, right? I don't have to flip it because grams of solution are going to cancel out if I leave it as is. So that 10 to the 9 is on the bottom. That 0.10 is on the top, grams of arsenic. Okay, punch that into my calculator. I get 2.5 times 10 to the negative 8, or 0.0000000025, right? Kind of more conveniently represented in scientific notation since it's such a teeny tiny number. My units are my grams of arsenic. All right, and then sig figs actually worked out pretty well. 250 has 2, right? Why does it have 2 instead of 3? There's no decimal in the number, right? If I wanted this to be 3 sig figs, there would have been a dot right at the end there, but without that dot, there's only those 2 sig figs. And then the 0.10 also has 2, so that's my final answer. All right, and again, those parts per million, parts per billion, that's a very tiny number. This is about half full. This is probably about 250 grams of water, right? I can only have 2.5 times 10 to the negative 8 grams of arsenic in there before it starts negatively affecting your health, right? A very, very tiny number. And that's when you see these most often is environmental sciences when they're going and testing for contamination and stuff like that, where only a very small trace amount of these compounds are allowed in solution. Okay? All right, so, right, we finished up our solubility of gases, as well as the big thing today was talking about concentrations. This is the way that we can quantitatively talk about solutions, and in particular, how much solute there is dissolved in a given solution. Okay? We're going to be using this a lot in our math in the future, and in particular, molarity, because that's kind of the go-to, most convenient way to talk about reactions. Like I said, a lot of reactions happen in solution, so it's a very convenient unit.